Let's discuss about the measurement in quantum mechanics. There is a big problem while we do measurement in quantum mechanics because the process of measurement changes the system. Suppose we have an electron. If I want to see it, the photon will strike it and it will change its orientation, its configuration, its state is changed. So if initially the electron was in this state, I will not get any information about this state because the photon which strikes on the electron changes the system entirely. So this is a big problem in quantum mechanics. Now let us consider the example of measurement of energy. Suppose we have this Hamiltonian, we have this eigenvalue equation for this Hamiltonian where these chi's are the eigenstates of this particular Hamiltonian. We know that these eigenstates are orthonormal to each other. That means orthogonal and normalized. Orthogonal means they are perpendicular to each other. Normalized means their lengths are equal to 1. This is the energy eigenvalue when measured in the particular state psi I. And I can run from 1 to n. Now before measurement, I can write an arbitrary state which is denoted by psi as a mixture of these psi I states, and these ai are complex numbers, and modulus, ai square, if I write ai square, this gives me the probability or the contribution, percentage contribution coming from this psi I. Suppose this I is equal to 1, so a 1 mod square will give me the percentage contribution of psi 1 in making the state psi. And if I is equal to 10, which means a 10 mod square will give me the percentage of contribution of psi 10 in forming this psi arbitrary state. Now this state is a coherent superposition of all these eigenstates psi I, and this kind of state is called a pure state or pure ensemble. An ensemble is a collection of systems which are identically prepared. Before I proceed further, let me give a few minutes to this ensemble. Let's discuss about ensembles. Actually, an ensemble is supposed to be characterized by one particular state gate, say alpha. If we think about silver atom Ag47, so there are 47 electrons. If this silver atom is subjected to a magnetic field, then all the 47 electrons are pointing towards the external magnetic field. Their spins are now parallel to this magnetic field. So every atom in the spin has its spin pointing in the same direction, and this direction is determined by the inhomogeneity of the magnetic field of the apparatus. So all the states, all the electronic spin states can be represented by this alpha. But we have not described yet about the quantum mechanical ensembles of physical systems for which say 60% of the states are characterized by alpha and the remaining 40% are characterized by some other state vector beta. Now if we want to illustrate this quite a bit, so let's take about such atoms having random spin orientations, which means there should be no preferred direction associated with such an ensemble of atoms. So for that system, the most general state ket for an electron, which is a spin half system, can be written as some electrons are aligned parallel to the field, some electrons are aligned anti-parallel to the field. So for these electrons, spin is plus half h cross. For these electrons, spin is minus half h cross. Now there is a big important question that the question is this equation capable of describing a collection of atoms with random spin orientations? The answer is no. This equation characterizes a state vector whose spin is pointing in some definite direction. Namely, that direction is the direction of n. Now if for this direction, associated with direction, the polar and azimuthal angles, they are represented by alpha, they are represented by beta and alpha respectively. This is a polar angle, this is azimuthal angle. So we can write that C plus by C minus equal to cos beta by 2 to the power I alpha. This is a very standard formula. We are not going to derive this for the time being, but this is quite standard. Let the polar and azimuthal angle, which characterizes this direction n, be beta and alpha respectively, and we start with this 1 0, that is spin up spinner. First we rotate about this axis, y axis, then a second rotation is given about the z axis, and this is my desired position, and this is equivalent to applying this to this spinner, then applying this, and this is my net result. In this context, a very important concept we must discuss, which is the fractional population or the probability wave, because this is to tackle the situation just we have discussed that we do not have any definite spin direction, all the directions are random. We have some atoms which are having random spin orientation. So an ensemble or a beam of silver atoms we are coming out of hot oven is a very good example of this kind of random ensemble. So we can think of the spin orientations of that beam as a collection of silver atoms in which 50% of the members of the ensemble, which are characterized by this plus ket, 50%, remaining 50% are characterized by this minus. And for that particular ensemble, we assign some real numbers, this W plus equal to 0.5 and W minus for 0.5. These are called fractional population for spin up and spin down respectively. And as there is no preferred direction for such a beam, this is quite reasonable to expect that same ensemble can be regarded equally well as a 50% mixture of these states. Now, one thing I would like to mention, that here we are introducing two real numbers, W plus and W minus. But we do not have any information on the relative phase between the spin up and spin down cats. And we refer this situation as an incoherent mixture of spin up and spin down state. Now, one more thing is, we must not confuse this W plus and W minus with this C plus mod square and C minus mod square. This is not. Now, the probability concept associated with this W plus W minus, these real numbers, they are very close to classical probability theory. And the situation we encounter while dealing with the silver atoms which are coming directly from the hot oven may be compared with my class. If we randomly pick up a student, then there is a probability of the student being male is half or female is half. So 50% of the, say 50% of my class are male and 50% of my class are female. Now we cannot think about coherent linear superposition of male and female with a particular phase relation. And this kind of silver atom coming out from directly from hot ovens, where this W plus and W minus, these fractional populations are associated, this is called unpolarized beam, as there is no fixed direction associated with. But in contrast, if we think about Stern-Gerlach experiment, the atoms used in Stern-Gerlach experiment, where the silver atoms are subjected to a magnetic field and their spin orientations are not random, they are aligned along the magnetic field direction, that is called a polarized beam, and that is a very good example of a pure ensemble. A complete random ensemble and a complete pure ensemble can be regarded as two extremes of what is called a mixed ensemble. In a mixed ensemble, a certain fraction, for example 70%, of the members could be characterized by alpha, and the remaining 30% of the members can be characterized by the ket beta. In such a case, we may call that beam as partially polarized. Here, alpha and beta need not be orthogonal. For example, we may have an ensemble of atoms with random spin orientations where 70% of the spin is in the positive x direction and 30% will be in the negative z direction.